How's it going? Well, a lot of people here today. Must be the storm. Snow. Or long weekend. Yeah. Oh, I see the traveling from long weekend. Yeah, so there's no class on Tuesday, right? Yeah. And your projects are due today? Today, yeah. They all done? Yeah. Good. Anything I should know about? Anything going on? Any questions about anything? No? Did you guys, so I saw a bunch of you posted this discussion post thing. I'm kind of playing around with the discussion forum and what the best way is to use it to enhance your learning experience. I think it's a really interesting opportunity because it kind of gives you guys a chance for peer-to-peer interactions. And I think, like I said this before, I think one of the awesomest things about taking this course now as opposed to like watching videos or reading the textbook on your own is that you have each other. And so I thought it would be fun to do this kind of exercise of defining a problem in a setting where you can sort of respond to each other. So I was reading through some of them last night. There's actually one I wanted to highlight because I thought it was pretty well done. It also kind of dovetails with some research in my group. So this is somebody's state, I don't know actually who Adgelin is. Are you here, Adgelin? No? Maybe? Don't want to admit to it? You. Thank you. So, so this is the post that you put up for Minecraft. So this is a game. If you've ever seen it before, you're like this little guy and you're building towers and farming and stuff. And then there's these zombies that come and attack you and you're trying to protect yourself. So you can build weapons and fortifications and all kinds of things like that. So this is one way to formalize the Minecraft state space, which is what we asked you to do in the discussion post. So what I liked about this was the way that it broke down the different parts of the formalization sort of in the way that we've been doing. There's some humor. Humor's okay. So the state space, the space is sort of the Minecraft world, so all of the zombies and blocks and everything else. And then the AI player kind of enters in the world. The action set is all the things you can do in Minecraft. So there's actually quite a lot of these things. Jumping, attacking, placing blocks, crafting things. You can make bread and pickaxes and this very large variety of things. The transition models the laws of the Minecraft universe, which is very complex and very difficult to encode. So similar to our Windows domain, there's this big pile of code that's Minecraft that is basically its main job is to encode the transition model. So this kind of search is very large and it's very hard to put into our AI program without having all of AI craft in the inner loop. And then the cost function is time. So you want to reach your goal, whatever it is, as quickly as possible. And your goal test, well, you can pick lots of different goal tests. So you pick diamond. I actually know diamonds were in Minecraft. But anyway, diamonds you can sort of mine for stuff in the environment. So I thought this was interesting as a nice way to sort of formalize the state space, kind of showing you an example of what we're looking for or what I'm looking for in these discussion posts. And it also ties into some research that we're doing in my group. So Minecraft is interesting. So I'm going to show you a video of something my students have been working on. So this is what Minecraft looks like. And this is our little AI agent. And what he's trying to do is get to the purple square right there. And he's basically doing inference planning. It's going to just loop over again to figure out like which actions to take to put the block to get across this trench. This is a trench you can't really jump across, so you have to place a block somewhere. You know, and our very first approach to solving this problem, to making this little Minecraft AI, was essentially breadth first search. So we were expanding all of the search nodes. We were thinking like so sort of the search space was like, should I put the block here, and then all the places I could go. And did I reach the goal? No. Should I put the block here? All the places I could go. Did I reach the goal? No. And eventually it figured out if I put the block here, then I could find a trajectory to actually reach the goal. And one of our research objectives in this is to try to make it so that we're not thinking about, when we want to reach a goal over here, we're not doing breadth first search and thinking about the block in the corner, but really trying to focus on putting the block in the trench to get across, to reach the goal. So this is showing, I guess, how some of the things we've talked about already and some of the problems that at least one of you think is an interesting problem shows up in AI research. And the reason that we're using Minecraft, even though it kind of seems like a silly game, is it's actually a really interesting model for a lot of real-world robotic problems. So if you imagine a lot of settings in the factory and manufacturing. You're kind of building stuff, and we don't have a factory here at Brown in our robotics lab, but we can simulate some of the same problems in this Minecraft setting. So it's kind of a fun domain to be working in. And if you guys also remember the Microsoft tech support article paper we read last week, that author, that student, his name is Branavan, did a follow-on paper also about Minecraft. So it could read the Minecraft wiki and then figure out how to do things like make bread and pickaxes and things like that. So it's actually an active area of AI research, so nice job with the post. All right, so any other questions or comments about the discussion forum? Okay, we'll talk about it more in the next class. And I'm also interested in your feedback if you like this type of exercise and we should keep doing it, or if we should think of something else. So the topic for today, and we're kind of finishing up our unit on search. So the topic for today is adversarial search. So this is, what do you do when the world is against you? And there's somebody that's trying to, that wants the opposite of what you want. And so the sort of canonical example of this is like playing a game. So for example, chess is a sort of very old problem that's been studied for a long time. How can you make a computer that can play chess as well as possible? So here in this sort of fully deterministic space, you know all the possible moves that you can make, you know all the possible moves that your partner can make, and you're kind of assuming your partner knows what he's doing and wants to beat you, and you want to beat him or her, and you're just trying to pick the best move in order to win the game. So computer chess has a really long history. I recommend actually you read the Wikipedia page if you're interested in some kind of interesting stories about how the sort of different approaches people have made for it. This is one of the first computer chess players. Anybody heard of the Mechanical Turk? This is from 1770.
On Amazon.
On Amazon, yeah, but this is before Amazon. So this is why Amazon Mechanical Turk is called Amazon Mechanical Turk. So this was one of the first chess playing automatons, but the secret, anybody know the secret? Some of you? So the secret is, somebody want to tell me?
A person is actually underneath the table.
Yeah, so this was supposed to be like a little robotic guy that was playing chess automatically, and Europe was amazed, like, how could we have this automatic chess playing agent? But really, inside the little cupboard was a dwarf, a small person who, it was hard for people to believe that a person could actually fit inside there, who was pretty good at chess. And they had some way for this guy to see the board state, and then he could run some levers and stuff to make the little autonomous, the little guy, the fake guy on top, actually pick up the pieces and move the pieces. And so after quite a long time of this, people kind of figured it out, or they admitted that it was a hoax. And it actually wasn't an autonomous agent. But going back for a very long time, people have been very interested in these kinds of problems of how can we play chess and other games like that. And these problems are relevant also. So somebody at the very first lecture brought up like economics and Wall Street, these kinds of adversarial settings where you're trying to take actions and other people are also trying to take actions. And some of the algorithms and the ways of thinking that we're going to talk about are relevant in real world problems as well as gaming problems. So chess has come a long way since then. And the algorithms that we're going to talk about, some of them were even proposed for solving computer chess, although they're relevant to lots of other games too. And we since then had Deep Blue. So who's heard of Deep Blue? Most of you, yeah. So IBM made the basically kind of solves. I'll talk about what solved means. They made a chess playing agent that could beat a grandmaster. So Kasparov is a human grandmaster, and IBM is like the same people who made Watson. Made a series of computer chess programs that tried to beat human players, and there's this interesting history of the competitions and stuff, going back to the 1950s when Turing published a paper with the first chess playing program written, and in 1996 there's this tournament where Deep Blue played Kasparov, who was the human world champion, and Kasparov lost. This is the game, the end position. So Kasparov was black. And deep blue checkmates him here with the rook. So what we're going to talk about today is techniques that you can use to make a computer program beat people at games like chess. And you guys have seen some of this before in 17, I think. So Minimax and alpha beta pruning. So what I want to do today, we're going to review Minimax, and then we're going to talk about an extension to it, which lets you search more efficiently, which means you can search deeper. So in a lot of these domains, the trick is how far and how fast can you search in order to pick the best moves possible in a limited amount of time. So Minimax, so we'll talk about how you can do better than that using alpha beta pruning. Then we're going to talk about evaluation functions, which is where in modern computer chess a lot of the magic happens, where when you can't go all the way to the root of the search tree and figure out the best move. When you have to stop, how can you estimate how good a state actually is? So I kind of talked about solving computer chess, but we haven't actually really solved chess in the sense that we don't know if it's possible for two players who are playing chess optimally to win or lose. So what I mean, so let's take another example. Like, so we're going to work with tic-tac-toe today when we start to program. So if you have two players who are playing tic-tac-toe, and they're really good, what's going to happen? A draw, yeah, and we know that. There's not a way for either the X or the O to force a win in tic-tac-toe. It's going to be a draw. So for chess, there's a similar answer, right? Like for black and white, either there's a way for black to force a win, or there's a way for white to force a win, or there's a way, or like tic-tac-toe, you can know that there's a draw if both players are playing optimally. But nobody knows what the answer is, even though it's deterministic, and we kind of could know if we had lots and lots of computation. And the reason nobody knows is the state space for chess is too big to actually search through the entire tree and get to the leaves and figure out what happens if you have sort of two players who are acting optimally. Goes all the way to the root. And so the techniques even though we're going to work with tic-tac-toe, the sort of real situation is games like chess where you actually can't, like in tic-tac-toe, we kind of know if we act optimally, we're going to be in a draw. For chess and other games with larger state spaces, we have to figure out what to do even if we can't search all the way to the root and come up with a strategy. Okay. So the next thing we're going to do is formalize the adversarial search problem, sort of the same way we were doing last time with online search and local search and sort of our classical search approaches. So an adversarial search problem is kind of similar to our classical search. We have an initial state, but we have to add to that the player. So this is which player is moving at state S. Then the action, so the set of legal moves in state S. So let's take tic-tac-toe. What's the set of legal moves in tic-tac-toe for a particular state? If it's X's move. Yeah.
All the empty places.
Yeah, it's all the empty places that you can put an X. Or did I say it was X's move? Yeah, okay. So all the empty places where you can put an X, and then after that, it's all the empty places where you can put an O. Then we have the transition model. So once I decide I'm going to take action 1, it's going to update the game board and move me there. And then a terminal test. So for tic-tac-toe, what's our terminal test? Yep.
Either all the places filled or someone gets 3 in a row.
Right. So yeah. So the game is, so either all of my rows are filled, there's no more moves left, or there's a draw, or somebody wins. There's 3 in a row, and then we stop playing because they won. Okay. The final thing is this utility. So I kind of told you already, but like, what's the utility for tic-tac-toe? For X. Well, it's a function that takes a state and a player. So you have to tell me what it is for different states. Yeah.
I mean, I guess it depends game to game, but in tic-tac-toe, a good way of valuing the board would be how many 2 in a rows you have, or how many twos with a space in between you have. Something like that, I guess.
Yeah, so this is like a heuristic function. That's how good the board is. But what I'm interested in the utility function, it's kind of related to terminal test, but it's sort of like at the end of the games. So the terminal test is like either there's 3 in a row or the board's all filled. But the utility function is going to tell me how good my terminal state is in real life. Like what does it mean for X to win or lose or draw? So does anybody want to try again for the utility function? Yeah.
I mean, like you could say 1 would be a win, and like
Yep.
half would be a draw, and 0 would be a loss.
Sure. Yep. So if there's 3 in a row for X, then it's a 1. If it's a if it's a draw, it's half, and if it's 0, it's a draw. We're actually going to use -1, 0, and 1, but that would work as well when we code it up. So something that numerically encodes what's good for X and what's bad for X. And we think a draw is better than a loss, and a win is the best thing of all. Okay, so when we're doing this, we have a tree of states, right? So so this is showing part of the game tree for tic-tac-toe, where at each level, X and then alternating X and Y, each player gets to choose a move. So here's the top level where the board's empty, and the actions here are all the different places I could put an X. So and then that puts me into a new state, and now O gets to choose, and we're just going to expand one branch of this. And these are all the different places that I could put an O. And then it's X's turn again, and we kind of go down, and eventually we get to a terminal state. So it works out the same, whatever you use, but so we'll just follow the book and use -1, 0, and 1. So this is sort of an example of what it looks like to explore the game tree and what our algorithms are going to be doing, what space we're going to be searching in. So my next question for you guys is, what does a solution look like to tic-tac-toe and these games in general, chess? What's it going to consist of? Oh, wait, somebody else raised their hand. You. Thanks. I'm sorry, guys, but I'm trying to call on wider varieties of people. Yes?
Instead of like a
Yeah.
sequence of actions, would it be like a tree of actions?
Yeah, so this is exactly. So this is like the distinction that we made last week between plans and policies. A solution, since you can't control what your opponent's going to do, you have to be prepared for whatever happens. So we have to come up with a strategy that's going to work in any situation, not just a sequence of moves where we just close our eyes and hope that somehow leads to the best play, to the best state. Okay. So this is this is the slide from last time, plans versus policy. So we have to have some kind of policy or strategy, a tree of actions that says what to do. All right, so here is an example of a simpler game than tic-tac-toe, where we can write out the entire search tree. So this is like a really kind of boring game. So the first guy gets to pick A1, A2, or A3. And then the next guy gets to pick B1, B2, or B3 if they picked A1, or C1, C2, C3 if they picked A2, or D1, D2, D3 if they picked A3. And then at the end, these are the rewards that the first guy gets. Okay? Does that make sense? Does that sound like a fun game? No, not really. But it's good it's nice because it's not a fun game because it's so small, it's just boring. But the reason it's nice to talk about it in our AI class is because it's so small, we can actually put the entire tree up here and think about what our algorithms are supposed to do as they explore this tree. So what should Max do? A1, yeah, why? It says here in the caption. So like, what if we did A3? Look, there's a 14 down there, right? But there's a 2, yeah. So what's wrong with that 2? Everybody see the 2? Yeah?
I mean, the other player given his choice of those 3 moves is probably going
Yeah, so even though that 14 is like so tempting, this guy, if we assume that Min is going to act optimally, this guy is never going to pick it. So this 14 is just a false hope. So we want to do A1 because the minimum value of this which is 3, is larger than the minimum value of this, which is 2, or the minimum value here, which is 2. Does that make sense to everybody? So we don't want to look at like where's our best value, because our adversary will hurt us if we do that. Like he'll come and say, oh, you want that 14? Ha ha ha, I'm going to go pick the 2 instead. So that's why this algorithm, Minimax, is called Minimax, because you're alternating between minimizing and maximizing. Maximizing when it's your move, and minimizing to simulate what your opponent's going to do when it's their move. Yes?
What is this numbers?
What is these numbers? These numbers? Which?
No, on the leaf.
The leaf, yeah. So this is part of the game definition. It's the utility function for the game. So it's how good that state is for max. Make sense? Yeah.
I mean, so this is like a simple game.
Yeah.
Where a win for me is automatically a loss for the other person, and like a bigger win is a bigger loss.
Yeah, right.
And it gets a lot more complicated if that 14 also gives the other opponent some points and more points than
Well, you could, so assuming it's still deterministic, let's say that like, 14 and your opponent, you get 14 and your opponent gets 7, you could subtract them, and the net, it sort of depends also what your goal is, right? So like maybe you just want to get as many points for yourself, and your opponent doesn't wants to get as many points for themselves, and they don't really care how many points you get. They just want as much as possible. So what's called, so this is like a zero-sum game, not a zero-sum game. Then you get different strategies. They might decide to collaborate and both get lots of points. It's like the prisoner's dilemma, where you sort of have to decide, and there's lots of theories and arguing about the best strategy in those kinds of situations, which we're not going to talk about today, but it's really interesting stuff if you're interested in exploring in more detail. Okay, so we're going to talk about zero-sum games where your win is the other guy's loss. So we're going to assume that Min wants you to get as few points as possible. He's out to hurt you. And you could decide, like you could sort of invert the value function and say he's out to and switch min and max, and it would be symmetric. But we're just going to since it's symmetric, we'll just pick max as the player we're going to be talking about. All right, so now let's implement Minimax. So here's the pseudocode, and I'm going to pull up the, what? Okay. So this is interesting because I heard you say recursion. It's a recursive formulation.
The mutually recursive version of it.
The what?
The mutually recursive.
Yes.
It's easier.
Yes. It's nice and short. Set default fonts. All right. Everybody see? Yes? Okay, so here is our Minimax guy, and I had defined, let me just blow through what we're given. So this is like our tic-tac-toe state. So it tells us the board state, which is just an array of integers. We have methods to find out what moves are available. So we're just checking which is empty and pulling up the moves. We have methods to, given a move, give you a new state that applies that move. So I'm going to talk about this a little bit. It's kind of a coding trick that is worth keeping in mind. So we could have, if we said move, self, player, move, we could have modified self, right? Modified our own game board with that new state. But we're not doing that. What are we doing instead? Anybody want to read the code and tell me in words what that's doing? Yes?
We're creating a new board that's identical to the old board and then adding.
Yeah, we're creating a new board. So here we're making a new board that's identical to the old board with this new move. So we're not modifying our current board state at all. We're just returning a new state with a new board state with that new move. Does anybody want to tell me why that's a good way to do it? Yeah.
And then if you're doing like a breadth first search, you can still like go back.
Yes. Yeah, exactly. So this way you don't have to worry about changing the values of your boards from underneath you if you're going back up in your search tree. So this is a very common design pattern called like immutability. So I'm making my board class immutable. Nothing can, once I create a board, nothing can change it. Yes? What's that?
NA.array there. In Python, does it just make it an array?
This is making a copy of the board.
NumPy?
NumPy, yeah.
Oh, it's called NumPy?
That's why I don't know what people call it. I call it NumPy.
It sounds funny.
NumPy.
Alright.
Yeah, it's NumPy. Yeah, so I just imported.
NumPy?
What's that?
What was he saying?
Oh, so the library that I'm using to make the array, this isn't too important to understand the whole algorithm, but the library that I'm using to make the array is called NumPy, N-U-M-P-Y, which I pronounce NumPy. I don't know if what you're supposed to pronounce it as, but I think NumPy is more fun sounding than NumPy. And it's a pretty useful library if you haven't used it before. I don't know if we require to use it in the problem set in the project, do we? No. You might see it in the uncertainty one. It's nice because it lets you do really fast matrix multiplications and things like that. And it lets you do nice array indexing, which is why I used it here. But not critical to understand the algorithm. The main thing to know is it's a game board, it's 3 by 3, and there's indexes to get stuff on the board. All right, I just wanted to call your attention to the fact that we're doing this in an immutable style. Okay, so here is our Minimax guy, and the Minimax implementation is empty. But what we're going to do is play tic-tac-toe, and why don't I switch it back to an empty state. And it's not going to run right now because Minimax decision here is empty. So let's define something. So Minimax decision, this is going to be the thing that does our inference. And it takes as input the state of the game and the player who's playing this game. And what we're going to do first is something really stupid. We're going to choose a move randomly from all the moves that there are in that state. And then what this outer loop is doing is it's just a bunch of code. So here it's calling the algorithm for x, and we're letting the computer be x. It's very generous of us. Let him go first. And then we're going to get our move for O. So this is a bunch of code to get our move. And then we make that move, and then we print out the winner at the end. So let's try that. So here is what it looks like when we run. So X's move, and an empty game board, he picked 2, 0. So this is this is like a tic-tac-toe board. This is just sort of showing you what it looks like as we play. So X is down there, and now O's move is here. So X is here. We get to type a number to say which place we want to go. What should we do? 6. I heard 6 first. All right. So wait, what happened? Yeah, 6. So here's our 6, and then X picked a move here, and now it's O's move again. Make sense? So X picked a random move.
I would take 5. I want to see.
5 doesn't do it.
Okay, let's try 5 and hope that X. Oh, X got lucky. Thanks, guys. What's that? All right, so we try again. Let's try. So let's try to win this time. So X went. So X went down here. They didn't try to block us. So should we win? Yeah, let's win.
Oh, yeah.
So we won that time. So this is just going to pick randomly. And we can beat it pretty easily. Okay? So now let's see if we can do better than a random tic-tac-toe player. All right, and the implementation style we're going to do, here's the pseudocode for it. We put it up in bigger text. So it's a mutually recursive algorithm. So we're going to have these 2 functions, min value and max value. So min value is what the other guy is going to do, in this case us, and max value is what the computer is going to do. So we're going to just alternate between thinking about what we're going to do and then thinking about what the other guy is going to do. We're going to go all the way down to the root of the tree. So we check if we're at the root, and then we return the utility. Otherwise, we pick a move, and here in actions, we just pick all of them. We try all of them, and we call our little helper function to do it. So, all right, so what should we do? Let me try to put this up at the same time. So what should we do first?
Iterate all the actions.
Yeah, we should iterate through all the actions. So I'm going to call them moves. State dot moves. And then what should we do? So we have a move here. Yeah. So let's set some bookkeeping variables. So best move equals none, and best value equals. I'm just going to do none because I always get confused about the signs. It's a little extra in the if statement though. So now we're gonna get a value from somewhere. We don't know what. Let's just say none for now. And then if what?
If value.
Yeah, if value is greater than best value or best value is none, best value equals value, and best move equals move. And then what do we do next?
Your
What?
Values.
Oh, sorry. All right, and why is this complaining? Never used. What do we do next?
I guess if this is just one layer of decision, return best move.
Yeah, return best move. All right, so now it all depends on getting that right value. So how do we get the value? Yeah.
One of the utility.
Yeah, we need to write one of our mutually recursive functions. So which one are we going to write? Which one are we going to call? Well, what do we, yeah, that's right, max first, but what is this outer for loop doing?
If you use a maximizer, then you should call your minimizer.
Yeah, we should call our minimizer. That's right. Make sense? Yes?
How do we know our utility function isn't such that we want to minimize everything and we're the minimizer?
We just decided. So we have to make sure, we have to be consistent. We have to decide at the beginning whether we want to win or lose. Or another way to say that is when we define the problem, we have to decide what the utility function is. And if we just pick it to be -1, 0, and 1 for x, then that corresponds to the rules of tic-tac-toe. But we could decide that we're going to play another game, let's call it tic-tac-whoa, where your goal is to put x's in all the corners, let's say. And yeah, so so that would correspond to a different utility function. It might be a pretty difficult game to win unless you had a cooperative but you really get to decide that as part of the problem statement. And I'm emphasizing this again because a lot of the magic of AI is define the problem in the right way. So don't feel tied to tic-tac-toe if you don't like it. All right, so let's write our minimizer. So what should the function specification for it be? It's up there in the pseudocode. What's that?
Takes in the states.
Well, yeah. So let's call. Okay, I was gonna say what's the name? Min value takes in a state. And I'm gonna also pass in the player. So I was trying to decide if there's a way to not have to pass in the player. I think there was if I stuck the player in the state. But what I liked about it was that it lets you, when you make the function call, decide which player the computer is going to be without hard coding it. So I'm going to take in the state and the player. And now what do I do? So what's my general pattern for recursive functions? What do I do usually? Yeah?
Put it in check for the base case.
Yeah, put in check for the base case, and then what's the other part? Do the recursion case. Yeah. So I heard you say the right answer. I'm going to do my check for the base case. So if state dot is terminal, then return state dot utility player. And I've defined my utility to take in the player because if you're X, it's inverted from if you're O. So so there we go. So what next? Yeah. Yeah. So I'm gonna do a for loop, right? And inside each thing in the for loop, I'm gonna call max value. What am I gonna do my for loop over? Yeah.
It's hard to read.
It's hard to read. Yeah. Okay. Well, what do you think we should do our for loop over?
Oh,
Yeah, all the actions available in a particular state. So we're going to do our recursive case. So for move in state.moves. Is there a question? Yeah?
Wouldn't this be a really great problem to have to use some memory on?
To use some memory. So what do you mean?
I mean, when you first calculate the quality of a particular board state,
Yep.
wouldn't it be really great to store that somewhere so you don't have to recalculate it every time you move one state?
Yes, you are absolutely right. So the question is, wouldn't this be a great problem to use some memory on? So how many possible tic-tac-toe boards are there in the world? 9 factorial. So is that enough that we could fit them all in memory? Yeah, it's not that many. So we could just save all of our board states in a big array or a big database on disk, and then when we get a board state, we can look up the move, and we can instantaneously know what the right move is. And that idea is used a lot in gaming. So in tic-tac-toe, it's like, because it's so small that we can solve it, you don't even need to do any of this alpha beta pruning stuff. But to make the table in the first place, how would you do that?
The very first time you run through the calculations,
Yeah.
when you finish it, you would store it in.
Yeah, so you would still be doing alpha beta pruning or minimax in order to make the table in the first place. The other thing is, when you have a big game like chess, are you going to be able to store all of the moves in the table? Yes?
No.
No, yeah. Yeah?
You could store a few states ahead temporarily and then replace them with new ones as you go on. That way you have less recalculating to do each time.
Keep like a few rows of the tree.
So I think I get what you're saying. So as you get down to that game tree, so like the next move you maybe already searched in that space. Yeah. So I think that would help it run faster and search deeper. And what you're talking about is an example of a trick. I'm not trying to belittle it by calling it a trick. A lot of what we're doing is tricks. I think if alpha beta pruning itself is a trick to make Minimax work better. And what a modern chess program like Deep Blue, or the best one right now, is called Ribka. And I think it runs like on my like it could run on my laptop and beat Kasparov. The original Deep Blue was like on an IBM mainframe. And what these programs are is lots and lots and lots of tricks, like some of the ones that you're talking about. Another trick we're going to talk about towards the end of class is like, what do you do? So in this search, in tic-tac-toe, we're going to go all the way to the root of the tree to find the answer. What happens when you can't go to the root? What do? You stop early and use a heuristic, yeah. And how do you get that heuristic? Tricks, yes. And chess sometimes, so in chess, a common heuristic, like there's actually like a bunch of people who have solved chess for endgames. So like all the chess games with less than 5 pieces. We have a big book, a big database, a table that you can just put on your computer and look up what to do once you hit that endgame, once you get all the way to the leaf node. And there's also an opening book, because there's so few possible opening moves in chess. There's sort of opening moves that computers don't search to find. They just have a bunch of tricks given to it by grandmasters to tell it how to get off on the right track. So it doesn't have to search at the beginning. So I'm glad you're bringing this up, because there's sort of lots of stuff that happens to make a sort of competitive chess program, for example. For the sake of exploring this Minimax algorithm, though, we're not going to do tricks like that. We're just going to try to do the exhaustive search, because a lot of the tricks hang on this structure. So I want you guys to understand the structure of the algorithm. All right, so on that vein, we were doing this mutually recursive Minimax, and we're doing our min value function. So what do we want to do inside of this? Yep.
Call the max value.
Yeah, call the max value. So let's call max value state. So I have a way to move, given, I think it's the player first, and then the move. Let me look that up. Move. So here I'm using my immutability trick. I'm returning a new state and passing that one down the search tree instead of modifying my state, which gives you all kinds of really weird bugs, because some other recursive call will change the next recursive call. It's very confusing. So I'm making a new state to pass down the search tree, and I'm going to pass the player.
So, I have a question.
Yep.
When you pass in player to state.move,
Yep.
presumably it's the player who's moving.
Yes,
So that needs to alternate.
that's right.
But the utility player doesn't need to alternate. So how are you going to get?
That's right. So it actually, the way that I implemented it, the utility player needs to alternate for min because it's the utility for this player. You basically want the utility to be in the same units, but it does need to alternate when you're passing it down. So when we switch from min to max, we want to switch to the other player. So let's do that. Other player. Does that make sense? Okay. And we want to do this too, I think. Okay, so undefined name max value. So let's define it. State. What's that?
Yeah.
Don't you want to store?
Yeah, I want to store something. Good.
Yeah, but why is it other player, by the way, for the leaf node? Because isn't the leaf node the state you're already at? So you're at this plate where, yeah, never mind, I'm wrong.
It's because you're minimizing. So
Yeah, I got it.
yeah, I think I could have done this in a more elegant way and got rid of that
And we
bookkeeping,
need,
but
like, an initial value for value and to keep the
yes. So let's do that. So value equals.
There must be some Python.
What's?
There must be some Python function which does all of this.
Yeah.
Yeah, there is. There is a way. So I could do this in a list comprehension, and then I could do a numpy.argmin to do it all in one line. I just think this is clear if people haven't seen the Python triggering. So that's why I'm doing it this way. Yes? Is it supposed to be positive? It is supposed to be positive. Thank you. All right, so value equals, so let's see. So there's a problem, right? Min of value and max value. So let's say value equals this. And then what? Return value. All right, how does it look? Pretty good? What's that?
Size max value.
Size max value. So let's do max value. So basically the same thing, yeah. So if state dot, so we're going to do our base case test. Return state dot utility player. In this case, we're being ourselves, so we don't have to invert it. And then value, we just invert our signs, right? Inf for move in state dot moves.
But we passed in the other player to max value.
Yeah, isn't player the current? Yeah, if you're switching the player,
So
each recursive call doesn't matter.
you don't want to call state.other player in the max value call.
I don't want to call state dot other player. I think I wanted to call state dot other player
Everywhere?
Either
If you
everywhere
call it
or
everywhere, yeah.
On each recursive call, that would be
Yeah,
good.
that's what I did when I practiced
Okay.
this morning. So I don't actually have my recursive call up here. So let's add that. Min value of what?
You want to do?
Given the other players, we do state.other.
Yeah, I want to do state dot move player move state dot other player. So I want to switch my player.
Then you can get rid of the one at the top of min value in the state that you
You sure? I think I needed it.
Yeah.
You're returning utility for the max player. If it's
Yeah. Yeah, because the utility that I'm returning has to be in terms of my utility. So that's why I had to invert it for min, but not for max. So it's all in the same units. All right, so let's do this. So value equals what? Max. Yeah, so this is our max function. So we're going to return max of value, and then what? Min value, right? State dot move player move. State dot other player. So we're going to switch our players. And then we're going to return Turn value, comma. All right, what do we think? What? Should we try it?
Yes.
Yes. All right, so actually what I'm going to do is switch. So this is an empty board where we have to go all the way to the root. Let's try it on a simpler example where we don't have to go all the way to the root so we can see more easily if we're doing the right thing. So here's a board where they've almost all played, and it is this? It's X's move. This is wrong then, so I should add.
You're right.
It's O's move. And when this goes in, it's going to be X's move. So I'm going to take out an X and let him decide what to do. All right. C. X's move, and it picked X. That's good, right? It was better than a random guy that ignored the obvious win, right?
We only had a one.
We tried again.
Anyway.
What's that?
Exactly as bad as the random one.
What's that?
Well, it could be exactly as bad as the random one. We had to try it a couple more times to find out.
Okay, let's see. So this seems to be returning the same answer for multiple different runs. I have had Python programs that didn't due to a non-determinism in the Intel floating point chip. So I have had that happen, but in this case, we're not running into that problem. So now let's try a more interesting one. So let's take out some moves here. And let's see what he does. So it's X's move. It was here, and he picked this move. So that doesn't look so good, does it? No.
Right where you want to.
Yeah, so there's a bug somewhere. So if we do that, he wins. So we wanted him. So what did we want him to do?
Block off your
We want him to block off my my move there. So let's try and figure out what's going on.
I'm still totally convinced to state that other player that you have in the top of min value.
You think?
Yeah.
Let's try it.
Because you're switching the player and the initial call in the minimax decision, so player at that point is the other player already.
Right, and so you want the utility.
But that's why you want the utility to be the other way.
Value?
Yeah. So we're taking the vest, the min value.
Players belongs players.
Yeah, because you're looking for the same players.
But it flips each time.
I know,
Min
but
always gets
we're
player
flipping
two.
it each time in the recursive call. In the recursive call to min and max value,
Right, so when you get
we're
into min
switching the
player,
player
player
net.
is player.
No, player is the other player, always in min value.
Yeah.
And so you want to look at the utility for the first player. So you should flip it again.
I'll get out now.
Well, let's try it. I'm pretty sure that it's not it, but when in doubt, try it.
The first time we ran it, though,
Yeah?
it did win.
It did win, yeah.
Where it needed to go.
Yeah, so that was encouraging. See, so all right.
Because it couldn't have, I don't think it could lose.
So let's give ourselves like 5 minutes to figure this out. Otherwise, we'll switch to the code I wrote before class that I tested. Yes.
I had a question about the
Yeah.
utility function.
Yeah.
In case of a win, if the weight of that win,
Yeah.
I guess it's if you explore two different options where one branch will lead to an immediate win for one player, but then another branch you go all the way down and it might lead to a win for you later on. Does the weight of either do differently?
If it's an immediate win for one player versus you go all the way down and it's a win for you,
Actually, never mind. I can't answer that question.
you want it to go the other way, I think. Yeah.
Sorry, please scroll for a second.
Yep.
On the- Never mind.
Okay. All right, I keep hoping I'll see it. So let's give ourselves 5 minutes and let's try going back to our simpler example. So
Essentially, it's working on a single move, so it's probably not the min's fault.
what's that? So if it's working on a single move.
Like it's working on a base case.
Yeah, so it's probably, so if it's calling min.
What if we make max value change to other player when
Yeah,
you're
that's
returning?
fine.
Like return state for other player there.
Where?
Yeah.
In max value, return state early for the other player?
No, because the max value is in terms of our value.
Returning is always
Yeah.
flipped when you call max value.
Yeah.
So you get the
That's
first
right.
player.
That's right. Yeah.
And
All right.
that's not necessarily working on the other move.
What's that?
Thinking it's the wrong player and just trying to block.
So trying to let the other player in?
No. So like the reason it's completing the 3 X's in a row is because it has the wrong player and thinks it's an O and it's trying to block the 2 X's.
Or it's trying to win itself.
All right, I gotta look at my practice implementation, see what the if that looks any better. So here's what let's do a little comparison here. So min value.
You don't change this.
No, here we change. Did I change the state down here? No, I did.
State of other player should work regardless of which state you're in.
Yeah. New state. Oh, why is this one less than?
Just listen.
Best. Oh, I see. It's the other way around. Okay. Yay. And then here's my practice min value. I put some extra bookkeeping code on this one. Utility to other player.
Does state of other player work like regardless of which state it is?
Yeah, I think so. I tested it.
State the other player always returns X.
Well, like if the state encoded which player it was.
The min value, state to other player, state to other player. All right, I'm confused. It looks the same to me.
And maybe it's a problem with other players.
Maybe it's a problem with both of them. So what I'm going to do is try my other Minimax directly. And we'll see if that works. So import Minimax. Minimax dot.
So state.move doesn't.
What's that?
State.move doesn't change the player as a new state?
State.move does not change the player. Yeah, I think if I put this player in the state, we wouldn't have to do that player bookkeeping. So let me see.
Can we go back to the state where it's the lose?
Yes. So let's take out the O. Or wait, was that? If we block, no. I should have had more test cases.
And then take out the middle other top X.
I take out the top X. Okay. All right, X's move. All right, so no. All right, this is probably a bug in my utility function. I'm guessing it's in the game. Oh wait, no, it's fine. Okay, so it went from here. Oh, it didn't block my win. Yeah.
It's hitting for its player.
What's that?
It's hitting for its either player.
Yeah. All right, guys. So I'm suspecting now it's a bug in my winner here. So this is the code that figures out which player is the winner and which player is not the winner. So what's that?
Yeah, you can random if there is any.
So what's that? What's that?
It's taking time.
Yeah, so I'm just trying to run it from the beginning. So I didn't do exhaustive testing of this, but I did try a bunch of games, and at least all the test cases this morning seemed to pass. So yeah.
Do you think it could be too that it
No,
just
okay, that's not what it is.
Oh, never mind.
That's something totally different.
What?
So why is it a sensible move for Minimax, given the pseudocode of what we think?
No matter what.
What's that? What would you guys have rather it did as its first move? Intuitively. Center, yeah.
There are more possible wins. Yeah.
There's more possible wins to the center. Why will Minimax, assuming no bugs, will Minimax find that move or not?
No.
No.
Yes, but it'll stop first.
It'll stop first, yeah. What's that?
That there's more correct answers, or more ways to win versus ties. It just cares that there is a way to tie.
Right, exactly. Since the end of the game, you're going to tie anyway, it's actually not going to optimize for this case of this going to center. Why do we want to go in the center, though, as people? Yeah?
Because assuming the other player isn't an optimal player,
Right.
we can win.
Exactly. So there's kind of more ways to win. Intuitively, there's more branches down which we can win. It's easier for the other player to screw up if we go in the center. Yeah?
Wait, I realized for the case where we had the bug where it wasn't blocking the move, that it technically was making the right move, because even if it blocked the move, if the circle player puts it in the top right corner, then they've got a guaranteed win. So no matter what move it makes,
Oh.
Cases like this.
Hey. I think that would be really nice. So then so it was just that I picked a pathological test case. Yeah, okay. So maybe that means our algorithm isn't so toasted after all. All right, so do you want to switch back to our implementation then and see? Yeah. Let's do that.
Tic-tac-toe is too complicated.
Tic-tac-toe is too complicated. Well, it is complicated in that there are a lot of games, right? So here's our tic-tac-toe again. So let's just go to a simpler board where that definitely isn't the case. Let me turn that back on. Let's see what happens. All right, so what did he do? So he picked this move up here. So what should we do?
4.
We should do 4, but why don't we do 5 and see if he picks 4 in the next move? Okay? Oh. What's that?
Yeah, he's still able to force a win from this.
Oh, I see. So he doesn't care about winning. Yeah. So what should I do? I see. So either way. So if I block, he picks this. Okay. This is really interesting. Yeah. So you have a guaranteed win no matter. Does everybody make? So this wasn't the most elegant. The most elegant example of watching. I probably should have prepared a better test case that didn't get into this pathological case. But does everybody understand what happened here? And thank you very much for seeing that. I didn't see that. So does everybody understand what happened? It decided, like it could have picked this move right here and just won the game, but instead it decided to pick this move. And what was the reason for Minimax? The value, right. So in terms of like the value of this move versus this move.
Does your utility function only keep in track like 3 in a row, or does it involve like if there's 2 in a row?
It only keeps track of 3 in a row. Yeah. So this is just encoding the rules of tic-tac-toe. Yeah.
Quick question about utility functions versus just a general heuristic function.
Yep.
Is the utility function only applied to a terminal state?
Yes.
Okay.
Yeah. The utility function only works on a terminal state. It's part of the rules of the game. I can't play the game without the utility function because I don't know what it means to win. So if I'm playing tic-tac-whoa, I could with my corners, then I would have a different utility function, and that would give me a totally different strategy for what I'd be trying to do. Okay, so we did Minimax. I think it's working. I haven't tested everything, but I think
what it's doing is when it gets a guaranteed win, it's going to pick the lowest indexed move because you're starting at 0.
Yeah. So that's another trick that people use when playing these games, especially when you get to alpha beta pruning. It's going to pick the order that you consider the moves matters a lot. Because when we switch to alpha beta pruning, we're not searching the whole search space. If we can find a good move fast, we've saved a lot of time. So one of the places people use heuristics in these games is what order to search the moves, and then they try not to think about the moves that don't make sense, that aren't promising, for some definition of promising, like a heuristic. All right. So you guys have seen Minimax before in your 17. Is 17 the number? 18. What?
I fell out for 15.
Othello for 15. And Connect 4, people saw
Connect
Yeah,
4 or
Connect
a number
4
of other things.
a number of other things. All right. Hopefully this was still fun. Maybe. Yeah? Good. So the next thing we're going to do is talk about how we can do better than just Minimax. So do you think we can do better? Like, do you think we can do better? Yeah, we're talking about tricks we can do to improve performance. All right. Oh, here's like properties. So this is from is it complete? Yes, if the tree is finite. Are we guaranteed to find the optimal solution? Is it optimal? Yes, under an assumption though. Oh, there's lots of assumptions, but there's one that's particularly interesting. That the other player plays optimally. Okay. So this relates to this idea, why didn't it not care about moving to the center? Because it's just assuming that the other guy is going to do the optimal thing. So it doesn't really matter if it goes to the center or not in the center. But we know that people don't play optimally. So you can imagine building game algorithms that try to take that into account. And that would be better at beating people at tic-tac-toe than just straight up Minimax. So yes, against an optimal opponent. And then the time complexity is, so this is the notation from the sort of classical search, the branching factor raised to the depth of the search. So B to the M. And the space complexity is B times M. We're storing every single node as we're running through the space. Okay. So now let's talk about how we can do better. And to do that, we're going to use this really simple game, very boring game that we pulled up before, to do alpha-beta pruning. So the intuition behind alpha-beta pruning is that if we've found a move that looks pretty good, we don't need to even explore branches of the trees if we can prove that they're never going to come up with a move that's as good as the one that we've already found. So, sort of, you can sort of see this, and we'll see this play out in this example. Once we found this 3 move, we know, once we've gone all the way to the root of this branch in our search, we're going to know that all